Alright, so what we're learning today is we're learning how we can use calculus to perform optimization. So optimization could mean two things. It could mean A, we're looking at when we can get something towards maximum quantity, or B, we're looking at how we can get it towards minimum quantity. In addition to this, it could be we're looking for, let's say, displacement, so maximum distance away from an object or minimum distance away from an object. We could be looking at the maximum speed something is moving from an object or the minimum speed something's moving. In the case over here, consider we've got a lasagna tin. Does anyone like lasagna? Yeah. Good. Yeah. That's the correct answer. Lasagna is delicious. Okay, suppose we have a lasagna tin. You could make this tin simply by getting a piece of tin straight out of your metalwork class, and then using this singular tin, you could be like, pow, and you could punch a hole there or a square there, and you go pow again, punch another square there, and pow, and bang for the final one, because you're out of steam. And if you punch it, then you're able to fold your lasagna tin inward in such a way that these guys are punched out and you're able to bend the sheet metal. And what you end up with is a box of sorts where you can put your lasagna in to make your lasagna prior to cooking it. Does this make sense, how we're folding it? Yeah. Okay, now, suppose that our lasagna tin has dimensions of, this is 40 centimeters, and this is 25 centimeters. And the way in which we punch this out, these are little squares here where they're all equal to one another. The reason for this is if they're not equal, it won't fold into a tin. But we'll say that these squares are X centimeters. The question is, what size should these little squares be? So what measurement of X should we have to get the largest possible volume for our lasagna tin? Any ideas? What tool could we potentially use here to solve this problem at hand? Some form of branch of mathematics we could employ. Starts with C. Attaboy. Using calculus, we actually have a tool set that we can use to objectively state that we're going to get the maximum size lasagna tin. Now, find the length of X. Find the find the value of X, or the length of X that will yield the largest volume for the lasagna tin. Now the question is there some way that we could find out the volume here? Knowing that our base over here, the full sheet metal is X by, the full sheet metal width is 40 centimeters by 25 centimeters. And then we reduce it by 2 lots of X across here and 2 lots of X across here. What would be the area inside here in terms of X? Any ideas? Little Miss Forrest?
Is it just 40 times 25?
That's a good start.
Oh, wait.
It's going to be 40 by 25. Now the question is, how is that 40 going to be reduced? Knowing that we're cutting, bingo, how many parts of X? 2 lots of x. So the length is 40 minus 2 lots of x times 25, take 2 lots of x. Comprende? And then the volume is going to be, what's the height of our tin? X. Okay, here's our expression for volume. Now, if we bring out our handy dandy calculators and we go to our graphing mode over here, what we can do is we can put in our function that describes our volume. So do you guys want to open your calculators up to graphing mode? I guess that will have to do. Okay, so it's going to be x, 40 take 2 x's, and then it's going to be 25 take 2 x's. And we can graph it. And my calculator is not set up that great, so I'm going to go V window. No, I'm going to go V window, and I'm going to take it all the way across to, I just say 40. Zoom, auto, sort of, doesn't need to be that big. Let's go 30, zoom, auto, alright, cool, and that looks alright. So here's the function that describes the volume for any given size of x. Now starting off, if I trace this, these are my values of x here. So when I have x set to about 2 centimeters, my volume's 1,466 cubic centimeters. As x is increasing to about 6-ish, I'm going to get 2,157. If I take it back to 5, I get exactly 2,250. And if I keep going along, x gets really big. When x is approaching about 12 centimeters, I get 136. 12.3, I get 44 square centimeters. And then when x goes above 12-ish, so it's about 14, I get negative volume. Is it possible to have negative volume? Not really. I think it's just an artifact of math here. But the idea is our valid region for volume is in this first section here. So it's going to be between, come on, 0, well 0 we're not going to have any volume, and 12.5 where we have no volume. But between that sweet spot there, those values are going to give us positive volume, which is what we're after. Anything above 12.5, we're going to end up with negative volume until we get above 20, in which case we start getting positive volume, but we don't have any tin by that stage because we've cut all the tin away. So this part from here onwards is just rubbish. So what we can do is we can change our V window to only show the parts that we care about. 0 to 12.5, graph, zoom, auto. Does everyone understand what's happened there? Why anything above 12.5 is rubbish? It has negative volume. See how it dips below? The y value gives us the volume. Anything below the x-axis is just rubbish. It's an artifact of mathematics without context. So we only want to see the part that makes sense. So 0 to 12. All right, now looking at this, from visual inspection, what would be the best situation to be in? What value of x would be the best one to have?
The highest one.
Yeah, the highest value of y. So g-solve max. We know that the optimal size is going to be 5 centimeters. And that's great, but the problem is we're using a numerical method here. We're using our calculators to numerically solve for us. Is there a way we can use calculus to algebraically solve this value? Have a think. If we're thinking about calculus here, as x increases from 0 upward, it's got a positive gradient until it gets to its maximum peak, where it's got a 0 gradient, and then it's got a negative gradient here. If we took the first derivative, what could we be looking for to find that maximum peak, that local maxima? Let's take the first derivative and have a look. So we'll go options, calc, first derivative, y1, and send it. If you have a look, the derivative of our volume function is going to tell us volume with respect to time. How is volume changing as time increases? Sorry, how is volume changing as our value of x is changing? So you can see that it cuts the x-axis here. So you can discover that when your rate of change of your volume with respect to the change in the size of the x value, or the length of x, is 0, so when it's not changing anymore, then you're going to be either at a maximum volume or you're going to be at a minimum volume. In this case, it's only showing its maximum. So what we would find is that if we took this function over here, expanded it out, took the derivative with respect to x, set the derivative to 0 on the left-hand side, and then solve for x, we should get the optimal value for the length of x. That's a lot of working out and talking, isn't it? Let's just go for it and see what we get. Okay, so here's our function here. What would it look like expanded out? Well, it's going to be, and I'll probably need someone with their calculator in what you can call it mode, run matrix mode. What's 40 times 25? Leishman's on it.
No, I'm not.
Okay, he's not. Dylan's on it.
No, Dylan, use run matrix.
Run the matrix. Foreman's on it.
It's 1,000, so 1,000.
1,000? Okay, what's 40 times 2?
80.
Plus 2 times 25.
130.
And then, what's 2x times 2x?
4x squared.
Bingo. So here's our volume function in its expanded form. Now what we're going to do is we're going to take the derivative of this function with respect to changing x. So this is going to be the change in the volume with respect to the change in length of the value of x. This is going to be 1,000 minus 260 x's plus 12 x's. And then, when we discovered that our change in volume with respect to change in the length of x is equal to 0, in other words, it's not changing at all, it's either going to be at its maxima or its minima. So,
the 12 and x be 12x squared.
yes. Good catch. So what we can do is we can say let dv of x over dx equal 0. Why? V of x is optimized at dv of x over dx equals 0. So we end up getting this equation over here. 0 equals 1,000 minus 260 x plus 12x squared. Now at this point you've got a choice. If you wanted to, you can just use the solve feature on your calculators, so solve n, and you can solve for that equation. That's normally what I would do here, but if I know there's going to be an exact value, then I'd probably do it algebraically. We've already seen by a sneak peek that we're going to get exact values for our roots, aren't we? So what we can do is we can use the solve n function. So if you go up to, well, firstly you can find them all here in the graph mode. You just expand it out more. But because we're going to try and do this showing it blind, what we can do is we can go options, calc, solve n, 0 equals 1,000 minus 260 x's plus 12x squareds. We're solving for the x, and booyah. We get 5 and 50 over 3. If you state that you're using the calc or you use your calculator in any form of external exam or internal, if the question doesn't say how you have to solve it, you actually get scored preferably on the performance standards. You get CT4, which is all about calculator work. You demonstrate that you're using it to solve problems, you get scaled up on it. Oops, 5, or it was 50 over 3. Now the question is, which of these answers actually make sense? Think of the context of the problem here. 5 centimeters. Now, to make it more apparent, what are the values of x that we could actually have here? What would the domain be? 5 is fine, but what's the minimum value of x you could probably have? What happens if x is negative? No good. So our starting value for x could be 0 is less than x. So we're looking at 0, but we're not including it. What's the maximum value of x that's actually valid here?
12.5.
12.5. Was any more?
12.5.
Any more, it doesn't work because you've taken up too much, or you've taken too much tin away. So because of that, we have a domain. 0 is less than x is less than 12.5. So any answer we get out of our volume equation has to be within our domain. But does this progression make sense, guys? Okay. So, the lasagna tin is optimized. When x equals 5 centimeters in length. What is the size of the tin? How much volume does it have when x is 5? if you want to find this, you can either plug x equals 25 back into the, x equals 5 back into your equation.
You need the x out the front.
I should, but I'll just put it at the back because I forgot. And that will give you 2,250. Centimeters cubed. The other option is you can use your graphing feature in your calculator. These are already put in. You can simply go gsolve max, that one, and that will give you the same result if you've done all your algebra correctly. The difference is if you use the calculator in graphing mode, you're doing what I would call I'd call it a numerical solution, or you could call it a graphical solution, like when you were doing simultaneous equations in year 10 and you found the crossing zone. This is perfectly fine, and we use this a lot of the way when we're doing real world problems because it's just simpler to do it that way. But if you need precision, the calculus method is king, because that will have errors in it based on how well you can see. This one is just exact values if you want. The question is, do you understand the progression that's happened on the board here? If I said, Emma Porter, why did we take the derivative?
To get x.
We want to get x, but what's the purpose? What does the derivative tell us in this case? dv over dx, what does that mean? Think about it, what's volume?
Volume is the volume.
Volume, what does the d operator do to the volume? The change in rate of volume with respect to change in rate of x. How is the volume changing as the length of x is changing? Whenever you see the d operator, it means change in. Why are we looking for the change in volume with respect to the change in the length of x? That's the question. Why are we looking for this, Harrison? When is the volume optimized? Have a look on the screen. What is the slope of the volume function when it's optimized?
And it's high.
Max.
It's at its maximum. It's no longer going up. It's not going down. It's at the very peak. It's at its pinnacle of its volume. So why do we take the derivative and look for when the derivative is 0?
Because y is the highest.
Yeah, because when it's at its most optimized, the change is neither positive nor negative, it is purely 0. What about if we were looking for its minimum? If we were trying to optimize for something at its minimum, what would we look for here? Yeah, we'd take the derivative, find when it's 0, and then we'd observe where is it at its minima. If you find that it goes up and then it goes down, so it's a maxima and a minima, you'd have to look for where the minima actually is. But that's not in this question. Do we understand the progression, guys? The math is pretty simple for us. If I told you to do all of that, you wouldn't have any issue if I told you step by step. But do you understand why we're doing this?
Kind
Are there any questions? All right, this is a question in your investigation, but you're not doing a lasagna tin, you're doing a cake tin.
of. Is it round?
It could be.